Hello everybody. So my name is Manas and I am a student in 9th standard, and I developed an interest in machine learning a few months ago, and this is a series about my understanding of machine learning and neural networks. So today I will just go over where I started off. So I did something called linear regression. That's the first thing I think that everybody does. So I'll just explain it to you in this tutorial. Okay, so today we are going to do linear regression. You can see that. Okay. So linear regression basically means just putting a straight line through your data. So to give you an example, let's say we have a bunch of x and y values. Okay, so let's say x is 5, 3, 5, 4, 9, probably 6, 10, 7, 11, something like this. So now if you plot these points, they're going to look like this. So 3, 5, 4, 9, 6, 10 and 7, 11. So about this. Then let's just say we had a few more points, probably something like this. Okay. So now if I ask you to draw a line through this graph, probably you would end up with something like this, right? So our job is to tell the machine or tell the computer how to draw this line. So first off, we know that the formula of a line is y equals mx plus b. So if you have to draw this line, all we need to figure out is m and b, and then we already know the corresponding x that the user will input, and then we plot out the y. So with that we get the line. So first of all, let me just tell you where you can probably use linear regression. Your x can probably be some house prices in square feet of a house, and y could be like your house prices of that square feet. So let's say like 300 square feet, you have, I don't know, $500 or something like that. So if I ask you to plot it, it will look like this, and what this does is to an unknown point, let's say probably 2. Can you tell me what is the corresponding y value? So 2, if it plots this line, we know it's somewhere here, about 2.53. So, but we need to tell the computer how to do this. So what do we need to figure out? M and B. So let's measure how good or how best fitted our line is. So this line so our line should actually be going through all the points. That would be the best fit line. But on an average, if this is drawn, it's pretty good. So how do we measure the error or the loss? Will be this y value, this point's y value, the corresponding predicted y value, or the y hat, they call it. So this y value minus this y value, that will give you the difference, right? Because obviously that x is same, Euclidean distance, y minus y whole square. So that's going to give you the Euclidean distance. Sorry, what am I saying? Sorry, we're not measuring that. We're just measuring the difference in y, that how off our line is to the actual point. And we do that for all of these. And then you might notice that if we do this minus this, so y minus y hat, we probably get a positive value here. But if I do this here, where this is my y and this is my y hat, y minus y hat, because y hat is greater, I get a negative value. So we can't have error as a negative value. So what we do is, let me just probably erase this part. All you can do is you can take y minus y hat y minus y hat, and you square that. So any number squared will obviously give you a positive value. And then you can take the mean of that. Number of training examples, probably number of x points and number of points, basically points. So this is just taking the mean of all of these numbers, all of these differences squared. So this distance will be probably 1, 0.5, 2, 2.5, all of that, 1 square plus 2.5 square plus 2 square plus probably this seems like 3 square, and all of that. And you after you square it, you take the mean of that. So that's going to give you your loss. So let's just say this whole thing was our loss. So now we've defined the loss for our linear regression model. The most important thing is now we need to minimize this loss. So we need to optimize this M and B. In machine learning, M and B are usually called weights of your model, and B is called the bias. So now I'll show you how to minimize this loss using gradient descent. So I'll just clear up the board. Okay, so I'm going to go over gradient yeah. So gradient descent, and remember we need to find M and B corresponding to y equals mx plus b, right? We need to find this and this. We need to optimize that, and we defined our loss as the sum of I equals 0. I is just the training point value through I equals the last number of training points, y I minus y I hat whole square, and then you put 1 over n. So that's your loss function. So now to minimize this loss function, we initialize M and B randomly. So they can just be zeros, ones, whatever. Just there are a lot of initializations in machine learning frameworks like TensorFlow and NumPy, but you can explore that later on. So we just initialize this randomly, and if we plot out, now this is a very interesting part now. If we plot out a function of M versus loss, probably the function would, I'm just guessing a random function looking like this, like a W or something. So probably we picked a value of M at something about 100, so our loss was somewhere there. So now if I ask you, which direction do we need to move the local minima, or where the loss function is the least, is this point, I think, right here. So this loss is the least corresponding to some M value that we need to find. So that's how we get the optimizer, the best weights for our model. So we initialize it, let's say at 100, we get a loss somewhere here. So if I ask you which direction to move, you would probably say go down, right? So how do we know which direction? How do we tell the computer which direction to move? So there's something nice. We take a gradient at this point. Sorry, my gradients are very nice. We take the gradient or the slope at this point, and as you can see, the slope is increasing, right? So now I'm going to define an update function of M. M equals updated M minus, I'm going to define this alpha later on, they just call it slope of M. Okay, so slope of M, let's just look through this. The slope of M at this point is something positive, and by the way, learning rate is always positive, okay, never negative. So learning rate into some positive value will give you a positive value. So how are we updating M? M minus some positive value. So probably we're at 100, M minus probably 5 will make us go somewhere like 95. So, oh nice, we've come down here. Oh great. So now we again do gradient descent. At this point, it still seems that our gradient is increasing. So what do? We again do the same function and we start moving this way. and make this a nice concave function. Okay, we start moving this way. We start moving against the direction of the gradient, minus of the learning rate into the slope. So, but now you might be wondering, okay, we took m as 100, probably we're not that lucky, we take m as 1, we end up somewhere here. Now what do we do? Well, I'm going to ask you now, the gradient at this point is negative. So, now look at the beauty. Learning rate is positive, positive into negative is negative, negative into negative is positive. So, how are we updating m? M equals m plus some value, right? So, what's happening is 1 will get incremented or will be added to this number. So, m will start moving this way. M will become probably 2, then 3, so it will start moving this way, right? And then it will end up at this local minima. At the local minima, what's going to be the gradient? It's going to be a 0. So, this whole term will just cancel out. You will get m equals m minus 0, which is m. So, you are not updating any further after you've reached your local minima. So, that is gradient descent for optimizing m. Now, gradient descent for optimizing B is the same thing. All we do is, we change this to B, right? Probably our loss versus B would look something like this. And then, same thing, we start off here and we define B updates as B minus learning rate into the slope of B. So, we start moving here. Slope is negative, negative and negative will give you a positive, and B keeps on moving here. And you will reach your local minimum. If you start out at B somewhere here, then the slope will be positive and it will be B minus some positive value. So you will start moving this way. And you will reach the minima where your gradient will be 0. So that's how we have optimized our weights. So after we optimize our weights, the final values of m and b will be taken and put into this equation, and then it all comes back. Remember our earlier graph where we had all those points. I'm just drawing it randomly. It's going to draw some nice line through your data. So that was gradient descent for optimizing a linear regression algorithm, where we just had one feature. By the way, feature is your x and label is your y. So whatever you want to predict is usually your y, and features is x. So you can also say y equals some function of x. And then you optimize for m and b, and then you finally get this best fit line for your model. So quickly I'll tell you what we covered today. Y equals mx plus b, that's to calculate this line so that fits these data points the best, right? Then we defined our loss function, which was the difference, the y difference, and we squared it because we always need a positive value, and we take the mean of that. And then after this, by the way, this is called the mean squared error loss function. Once we take the mean squared error loss function, we minimize it using gradient descent. And I explained it to you, like you had the loss, you had m, you had b, you had some function, and you start minimizing, and then finally you reach your minimum. That's how we minimize this loss function. And at the end of probably, I don't know, 100, 200 iterations, but this is an iterative process, so by the end of 200 iterations or so, you would get good values for m and b that will make this line the best fit line. So that's all for today. Thank you for watching. Bye.